Today we're going to go over the process of reduction of order, a method to handle second order linear equations like this one we have here. A sub 2x y double prime plus a1x y prime plus y, or actually we can say plus a naught x y equals 0. That's a second order linear equation. And so we're going to go over the theory of the reduction of order technique, and then I'll follow that up with an example. Now I'm going to show the process of reduction of order. And again, we are trying to solve a second order linear equation. Something along these lines. a2x y double prime plus a1x y prime plus a naught x y equals 0. So we're solving a homogeneous version of this. And the first thing we need to do is to put this into standard form, or y double prime plus, I'll just stick with kind of standard notation here. We're dividing a1x by a2 of x. We usually call that p of x. And a naught divided by a2 of x, we usually call that just q of x. So we just end up with other functions of x, and that's just the notation we use. Alright, now we know y1x. We need to find y2 of x. And the idea is we can assume so we want y2 to be linearly independent from y1. So with that assumption, we can, or from that idea, we can think that y2 of x then equals some function of u of x times y1 of x. Why? Why can we say that? Because otherwise, y2 of x would have to be some sort of constant times y1 of x, implying that they're linearly dependent. And that's not good, right? That's not good. We don't want that. So we can't have that they're constant multiples of each other. So we can assume then that y2 is some function u times y1. So then what we'll do from there is that we will let y equal u y1. And if that's the case, then y prime is u y1 prime plus u prime y1, right, from product rule. And y double prime is the second derivative. So we'd have u y1 double prime plus u prime y1 prime. And then, so that's product rule on this first expression here. And then we'd have to do product rule again on my second expression here, and end up with u prime y1 prime plus u double prime y1. So again, that's product rule on my second term. And so we can combine that together if you want and get u y1 double prime plus 2u prime y1 prime plus u double prime y1. Okay. Great. So why does that really help us? So we're going to plug this into our equation again. Remember, we have y double prime plus p of x y prime plus q of x y equals 0. So I plug in all those expressions that I just had and factor. Well, let's just see. Let's just plug them in. So we get u y1 double prime plus 2u prime y1 prime plus y1 u double prime, okay, plus p of x times u y1 prime plus u prime y1, then plus q of x times, what is that, u y1 equals 0. Now here's the interesting thing. So we group together your terms that have just a u in them, So let's see, we have a u here, we have a u there, and a u there. So if I group those together, I end up with u times y1 double prime plus py1 prime plus qy1. And then the things I have left over, I have a u1 double prime, a y1 u double prime, and I have a bunch of things that are u prime, which would be, let's see, I have two y1 primes plus a py1 all times u prime, and that equals 0. Now, the reason I'm interested in this is because remember y1 is a solution. So in particular, a solution to what? A solution to this equation. So if I plug y1 into that equation, I get 0. And so this expression is equal to 0 because it's a solution to this equation. So then the result then we're left with just this y1 u double prime plus 2y1 prime plus py1 u prime equals 0. And here's our trick. We're going to let w be a new expression. We're going to let w be u prime. So then my equation becomes y1 w prime plus 2y1 plus py1 w equals 0. And this is why we call it reduction of order. I now have a first order linear equation. And actually this linear equation is not only first order, it's separable, so it may not be obvious to see, but this means y1 dw prime dx, or dw dx, plus 2y1 prime plus py1 w equals 0. And remember this is a dy1 dx as well. Okay, so if we multiply and divide by the appropriate terms, we end up with this equation. I'll write it over here. We end up with the equation dw over w plus 2y1 prime over y1 dx plus, I forgot my p, plus p dx equals 0. Okay, so now I can do some integration here. I'm going to end up with ln w and integrate. This is y1 prime over y1. That's a logarithm, so we have 2 ln y1 equals, I'm going to bring the p over on the other side because I don't really know what p is, but that's okay. So I'm going to have the integral, negative integral p of x dx plus some constant. And if I use my properties of logarithms here, I can bring these together to have ln of w y1 squared equals the ln of the negative integral. Or a better way of saying this is that w y1 squared equals another constant e to the integral p dx. Or w equals c1 e to the negative px dx divided by y1 squared. And so remember, w is u prime. So then I get back to u. U is the integral of all this, c1 integral of e to the negative px dx over y1 squared dx plus a c2. Okay. Now remember that my y is u of x times u1 of x, right? So then I can say y is all of this times y1. And here I'm free to make a little bit of a choice because I want to have solutions that are linearly independent. So what I'm going to do is I'm going to let C1 be 1 and C2 equals 0. And if that's the case, I'll try to write this a little nicer. My y2 then is this y1x times this expression here. So that's going to be the integral of e to the negative p of x dx all over y1 squared of x dx. And that's how you find your second solution. Okay, now I'll try to illustrate this with an example so it makes more sense, but it is worth knowing the theoretical version of this and to be able to trace through it yourself. Okay, so now as an example on how to use reduction of order, I'm going to use this example here. We have solve y double prime minus 4y prime plus 4y equals 0, and we're given that y1 equals e to the 2x. There are actually easier ways of solving this equation, but we need to use reduction of order to make sure our theory is sound. So remember, the assumption here is that y2, our second solution, is going to look like some function u of x times e to the 2x. And so for our notation purposes, we'll just call this y for the moment. All right, now with that, we need y prime and y double prime. And so we have to make sure we use product rule correctly. So y prime will be 2u e to the 2x. That's first times the derivative of the second, plus the second times the derivative of the first, so it's u prime e to the 2x. And then for y double prime, we just have to take the derivative of this, and keep in mind we have to use product rule again. So I have 4u e to the 2x plus 2u prime e to the 2x. And now we'll take the derivative of u prime e to the 2x, which will be 2u prime e to the 2x plus u double prime e to the 2x. And again, I'm having to use product rule on both of these. And notice I can combine here and have 4u e to the 2x plus 4u prime e to the 2x plus u double prime e to the 2x. Now I'm going to put this back into my original equation, and hopefully we can solve for u. So when I do that, I have 4u e to the 2x plus 4u prime e to the 2x plus u double prime e to the 2x. That's all of my y double prime. Now I need to have minus a 4y prime. So it'll be minus 4 times 2u e to the 2x plus u prime e to the 2x. And then I have to have a plus 4y, which would be my 4u e to the 2x. And all of this equals 0. Now, if you notice, some things are going to clean up. If I look at my u's, for example, I have 4u e to the 2x, a 4u to the e to the 2x, and a negative 8u to e to the 2x. So those are going to all cancel out. The same with my u primes. I have a 4u prime e to the 2x and a negative 4u prime e to the 2x. Those will cancel out as well. And so I'm actually left with u double prime e to the 2x equals 0. Okay, now as we know, e to the 2x will never be 0. I end up with then that u double prime equals 0. From here, we're going to do a substitution. I'm going to let w prime be u. Okay, if that's the case, then u double prime, I'm going to let w be u prime, then u double prime is w prime. So my equation then is actually w prime equals 0. So when I integrate both sides, I end up with w is the integral of 0. That's going to be a constant. And then, remember that's u prime. So when I integrate again, u is going to be the integral of c1 with respect to x. That's c1x plus another constant. So then I have it. My general solution, which is u e to the 2x, now is c1x e to the 2x plus c2 e to the 2x. And if you notice, this is what I started with, that's my y1, and this is what I just found, that's my y2. So there we have it. We solved our equation using reduction of order.